I'm going to talk about the series of experiments over this lecture and the next one, just covering a lot of different work that my group has done over the years, basically using the scanning tunneling microscope to look at different types of topological edge modes or boundary modes. So I guess, I look through the lectures and I see that you guys are all now theoretical experts of topological phases. So in terms of experiments, the number of experiments that actually probe these phases are actually not that many. They're very difficult to probe using transport experiments because often you're looking at some boundary states that you're trying to characterize and very hard to make electrical contact to. And I think this is a field which is, of course, mostly driven by theory, but in terms of experiments, many of the experiments have been surface-sensitive experiments like angle-resolved photo emission and STM experiments that I'll show you today and tomorrow. So my goal here is to first talk about today about sort of the old topological insulator experiments that has, sort of set the stage actually for maybe what will come in the second half of this lecture, some new experiments on Fermi arc compounds, Fermi Weyl semimetals. And then tomorrow I'll devote all-day lecture tomorrow talking about how we're using STM to look at Majorana end modes in magnetic system and superconducting systems. So, I don't know, there are some students here, so let's just start from the beginning. We use the STM. STM, is a device which is basically allows you to take atomic resolution images, but it's actually much, much more than that. In fact, if you go back and look at why the STM was invented by Binning and Rohr when they worked for IBM, was actually to build very reliable Josephson junction devices. They wanted a tool that could actually characterize superconductivity on the atomic scale, because IBM was making niobium oxide junctions, and the junctions were unreliable to make, nowadays you will call qubits. They're actually some of the similar technology, aluminum-based, that's being used for qubits. They wanted a tool which could actually characterize electronic structure on the atomic scale, and this was built actually off of a work of a person named Young, who actually worked, I think, in Colorado, not very far from here. He invented something called the Topography Meter, which was basically bringing a tip very close to a surface, and he had basically a mechanical jig to detect the tunneling current. And since tunneling is exponential as a function of distance, he had a very difficult time controlling basically his device using mechanical circuitry. And it wasn't until Binning and Rohr basically realized that you could use a piezoelectric element using feedback loops that you can stabilize vibrations, if you like, out of your measurement. And with that, you can have a tip which you have very good control of being above the surface. So you can measure the tunneling current, and you keep the tunneling current constant as you raster the tip across the surface, and you record the trajectory the tip takes to keep that tunneling current constant. So that's a STM topograph, and this is the very first one of them, which is an image of a silicon surface. You'll see the graphics has certainly improved over the years. And this is where it got started. Now, the very first STM which was actually built was a cryogenic STM, and the field sort of took a turn and built all kinds of different type of STM instruments. But a guy who really pushed the STM technology at low temperatures, which has become a workhorse, I think, in condensed matter physics these days, was actually Don Eigler at IBM Almaden. This is Don with his dog. And Don actually on the side trains dogs. And this is a picture, of course, you're all very familiar with. And this is basically taking iron atoms and manipulating them on the surface of copper and looking at surface electrons of copper with the STM and actually confining them using the scattering from these individual iron atoms. Now, this is actually where I got interested in the field. And the reason I put this up is that this is actually the very first example where we're actually using the STM to image, if you like, a wave function squared of a state that we can calculate. Okay? Of course, it's elementary, but from a technical point of view, it was a very eye-opening moment for many experimentalists that this tool can be used for all kinds of different materials. And this is kind of just a collage of pictures, for example, from work in our lab that we are very proud of, where we're basically essentially doing this very same experiment, if you like, with very increasing level of sophistication, not looking at particles in a box, but looking at, correlated electrons, superconductivity, magnetism. And I'm going to show you a lot of examples of that through these two lectures. So today, okay, so let me talk a little bit more about the technology. So the technology has improved since even the days of Don. Don is retired now. So we kind of have moved from the, so you can imagine that if you want to vibrationally isolate the system, you use a laser table. You guys have all seen, even the theorists have seen a laser table. So now this is a very crazy laser table. It weighs about 30 tons. So we take these instruments, and this is many places now around the world have these laboratories, where you take these instruments, which are sort of a bad marriage between low temperature physics, surface science, very ultra high vacuum environment, and you combine it very low vibrations. Okay, so here this is just a giant mass on a spring. Okay, and ask any question you like. Okay, and no question is stupid enough. Okay, yes. No, that's just the person has been shown for scale. This is just a drawing from our lab. You do have to go in from time to time, but that's a good question because you can see that there is a room around it. There is another room around it. So these are acoustic rooms. So essentially you isolate this system seismically, acoustically, and the vibration on this thing basically limits how much. I'll show you some examples. Essentially it's a noise in your tunneling current when you open this feedback loop. And that's the lower the noise you have, the more data you can take during the period of time you have before the helium runs out in your cryostat. Okay, yes? What's the acoustic access to? Oh, so this is a particular design where we actually made two chambers that were independent. This is one, and this is another one. And then we found that this doesn't actually work very well. This needs to be updated. So we basically made two rooms that are these are basically just acoustic panels. So acoustic panel is basically a material which is very absorbing. And you go in this room, you've been to a recording maybe studio. It's just filled with acoustic panels. Okay. Yes? No, you go ahead. Ask. So just think about your resonant frequency of your freshman physics, and just think of it as a filter. And when you basically go beyond the filter, you just get the 1 over omega squared. So what we do is this is not a stupid question. So what we do here is we take this resonance frequency, try to make it as low as possible. And we actually have stacks of different resonance frequency, and we make a microscope which is as stiff as possible. So its resonance frequency is very far away at very high frequencies. So then when you have something which is like, say, 0.8 hertz, by the time you get to 3 kilohertz, you have nothing. And that's basically why this works really well. So here's the, I could give you, this is one generation of instruments. So the idea is that you have ultra-high vacuum chambers. All the experiments I'll show you today and tomorrow, all the samples have to be prepared in situ. You cannot prepare a sample and take it out and put a probe on it. Once it's gone through air, forget it. You're not going to make reliable STM measurements. Everything is done in situ. Either you grow your sample inside, or you cleave the sample, as I will show you, for example, the first set of experiments that I will discuss today. And you can have tools besides STM to characterize your surface. Essentially, the UHV conditions here is very similar to angle resolved photo emission experiments. They also have to prepare very clean surfaces to do STM experiments. So all these rods, things you see, are just things to manipulate the samples around inside this environment. So we've gone to extremes in these instruments. For example, tomorrow I'll show you data from this series of instruments in which we can in situ kind of do molecular beam epitaxy inside this instrument, but also combine it with sort of preparing the tip that is sort of spin polarized. So imagine not just your sample you want to prepare, you can prepare your tip to have normal tip, superconducting tip, ferromagnetic tip, magnetic tip that you can manipulate with an external magnetic field, so you can get local magnetic information, and all of that can be brought together. Just while we are talking about technical things, so the way a STM experiment ends, I can see one STM expert in the audience. The way STM experiments ends is your tip crash into the sample. And it's very unfortunate because then you have to kind of prepare a new sample, prepare a new tip. So this is actually one of the things I forced my students to design. They were very much against it, to build a microscope that can receive multiple samples. And this allows us to have one sample that's sort of a sacrificial sample. We can always go on it, and we can apply very large voltages, sort of melt the end of the tip literally in situ to clean it and go back to the sample that we want to study. This basically increases our productivity, many, many folds, because to have to re-prepare a sample and move things around takes an enormously long time. Okay, so what's my plan today? So I pretty much told you about basics of STM. I'm going to talk about how we use STM to look at quasiparticles and their interference. And I already showed you the example from Dawn. Those are quasiparticles made on the surface states of copper. And I'm going to start on topological insulators, the sort of the Z2 topological surface states with Dirac fermions that are basically the first example of edge modes that we have found, for example, in 3D. I'm going to talk about how we use the STM to look at the absence of backscattering for these topological surface states. And then, of course, when this field got very started, we thought, oh, these things are absolutely immune to disorder. There was these ideas around for perhaps making very wildly beautiful conductors at the surface. But I'll show you that actually, of course, influence of disorder you can measure on these surface states, and it's very evident in our experiments. I'll show you an experiment that I don't get to talk about very often. It's a very, very simple experiment. But it shows that maybe these surface states actually transmit through barriers that stop other surface states, which is something that was fun. And I will show a digression of, these are mostly on 3D TIs. I will show a digression into a 2D TI with a 1D edge modes. And then hopefully I will have enough time to basically give a second half of a talk on basically a very recent experiment on wild semi-metals, which we have been working on, okay, and Dirac semi-metals. Okay, so today, basically, if I were to use an icon for today, this is what it's all about. You basically look at how electrons scatter from defects, and what can you learn from that? And I told you that the transport experiments often have difficulty probing these edge modes, which is why surface modes such as ARPAS and STM are useful here. But STM allows you to get more information than just the band structure. Okay, so we already talked about imaging, so spectroscopy. So the way we do a spectroscopy is we basically open the feedback loop. The tip sits on top of the surface at a given height, at a fixed height. You measure the tunneling rate, the conductance between the tip and the sample as a function of the voltage. And this is sort of just your garden variety semiconductor. This is gallium arsenide. And you see a gap. And of course, the power of the STM is you can do this experiment at every pixel of your experiment, of your surface. And with that, you can basically build essentially a local map of the density of states. So tunneling current basically between the tip and the sample is related to the integral of the density of states between say the Fermi energy and whatever voltage you apply between the tip and the sample, but it convolves the density of states of your tip and your sample together, okay? And so for this reason, for most experiments, we use very simple metals as our tip because we want the density of state of the tip to be extremely simple over the energy range which we want to study, we want to do our experiment. Once you've done that, then you basically have a measurement which is related to the density of states of the sample. And if the density of the sample, of course, varies spatially, for example, here's an example, you can do this measurement at a fixed voltage that gives you an energy resolved map of the electronic states in real space. And then you can turn that into a movie, of course, right? So and this is an example of basically the spectroscopic mapping in real space, actually of a surface of a topological insulator. So you can see as a function of energy, a lot of things happening in this picture. So figuring out what this means and how it relates to what we are interested in is basically mostly what we do. Okay, so let's start with this suppression of backscattering due to impurity. So very soon after discovery of TIs, basically our first task was to basically show that a forward-moving electron, when it hits an impurity, doesn't scatter into a backward-moving electron. You can look at this in a number of ways. You can either think about it, spin up doesn't go into spin down, or here's the article from Su-Chang Zhang, and in which they have this figure where they talk about basically this interference effect. If you think about how an electron goes around a single impurity when it's being backscattered, and these two paths giving you basically destructive interference. So let's look at an ordinary surface state. This is a piece of copper. So copper has these Shockley states, which have been known for a long time. They are basically like a 2D electron gas living on the surface of copper. And they have a parabolic dispersion, which have been measured previously using angle-resolved photon emission. And now if you come with the STM and just image a surface of copper, which has just a few defects on the surface, you can sort of see these interference patterns. Now, these measurements, as I told you, can be measured at different voltages. Okay? So you can think about this Fermi surface, or the band structure, rather, of this 2D electron gas, and think as I dial my energy up and down, I'm taking a cut. Okay? And the way to think about this experiment is the follows. I have an electron, if you like. I send it into the sample. I tunnel into the sample. It goes and hits a defect, and it comes back to me. And either it constructively interferes to give me a standing wave of up or low. And essentially, that's what's being imaged in these experiments. These are extremely slow experiments. Okay? Some of our experiments where we do maps of these sort of standing waves in novel materials, you're talking about 4 or 5 days, where you go to every pixel and record the very subtle modulation of the electron's density of state. That's a good question. So the susceptibility is the largest there, and that's basically what you're imaging in this experiment. Right. So you should, basically you should see some signal in here, but there is a signal there, but the signal is very weak compared to this very large susceptibility that you get when you're looking at right at the Fermi edge, if you like. Right. You're going to see a lot of examples of this as we go along. So this is just 2kF. So you can go to ARPIS and measure this at this energy and just read it off of this map. So this is a Fourier transform of these pictures. So this is quasiparticle interference. Okay? Yes?
Background of the light panels, particles,
good question. So this is just raw data that's just been Fourier transformed. So anything in your raw data, like you have a step edge nearby or something, that would give you some artifacts like that. You can clean these up. There are ways to clean them up, but I didn't clean them up. I just showed you just FFD of the maps with the color scale adjusted so you can see the most intense behavior. Any other question?
The middle circle, that's its radius is 2kF?
Its radius is 2kF.
But I don't understand, you can scatter from Fermi surface to Fermi surface at smaller values.
You can.
So why is that energy? Why is that?
So this is completely elastic. You're looking at a specific energy. You have an electron, and it's just giving you this scattering at this fixed energy.
So what corresponds to that? Different energies?
Different energies. So these are the fixed energy. So at a given energy, you look at basically if I put an electron at this energy, at this, it goes into some k vector on the Fermi surface, on the contours of constant energy. And then it can travel, it hits a defect, and it comes back to you, okay? So you have just Q1 and Q initial and Q final.
Select which, that's basically a selection of Fermi.
Yeah, contours of constant energy. The susceptibility is just very large there. It's large everywhere. So let's just look here. So I put an electron. I have a circle. Okay, so you can think about. You start here and you can end up everywhere. So it should give you a disk, right? But the 2kF wave vector, if you look at it, if you look at the scale, the susceptibility there is the largest. All of it is possible. Okay, and that's basically what this experiment measures. I'll show you lots of examples of this, and there are many ways to analyze this information. Okay, you can start with the Green's function, and you can do a T matrix calculation, and with your given band structure, and I'll show you some examples of that, and compute what the STM should measure. That's one approach you can take. It's just interference, right? So you have initial, just think about K initial, K final, you add them together and square it.
How large an effect is that? I mean, is it contrast to 1%?
No, it's large. Yeah, I don't have a color scale here. We can look at it. I can show you.
Of that order of 1%?
In copper, is larger than 1%. It's quite large. I don't remember the number. That's a good question then. Okay, so the way this experiment works is that you basically are typically running about, let's say, a nanoamp. That's actually quite a high current. So it's, think about an electron every nanosecond, roughly speaking, going from the, you're measuring, you're running a current. Okay, so you're measuring the conductance at a given energy, and then you change the energy. Yes. Excellent. So the energy resolution, there are many ways to characterize this. The energy resolution in tunneling is essentially determined by the temperature of your experiment, for the most part. If you really push quiet down all the electronic noises, which you can do. And the way you characterize that, I'll show you an example tomorrow. We use a superconducting gap, BCS density of state, to actually calibrate our temperatures. And that you can take the BCS and thermally convolve it, evolve it, and then you can compare to the experiment. Yes?
Sorry, one more question.
Yeah, no, it's good.
So, but your surface has those electrons have some Fermi energy. So they define, there's an energy of the ejected electron and the energy of sort of empty state to which you put that electron.
Okay, so I pull an electron from the tip into the sample, or I pull an electron out of the tip. So let's just look at that. So you change the voltage, so you can get a net current, but you can also modulate the voltage a little bit and just look at the small change in the current, and that's what the conductance that you're measuring. Yeah, the frequency doesn't really matter. It's very slow. But that's what you're looking at. You're looking at that's why the question was about the energy resolution. So you modulate the voltage and you measure a modulated current. And the finer your voltage that modulate, the finer energy resolution you have of any kind of density of states that variation.
But if you try to inject an electron, let's say some energy which corresponds to some momentum, and those states already filled.
So we can't, right? So we pull. So you reverse the bias and you pull those electrons.
Oh, I see.
So
that's why it's positive and negative.
Exactly, right. Good. Now you even understand STM. Okay, good. So let's talk about TI. So this is the first example of a three-dimensional TI. This goes back to the work of Kane and Millet, which basically realizing that pure antimony and pure bismuth have a inverted band structure relative to one another, and basically proposing that there was a range of alloy that you could make that you basically bring this inverted band structure such that you have basically a small band gap semiconductor. Okay, and these are experiments these are measurements from Hassan and Kava's group. These are transport measurements, basically showing that as you tune this material into this range of doping proposed, basically you end up with the resistance that instead of going down is actually going up as you cool it down. Okay, so this is the bulk properties, and this undoubtedly you have seen before. This is the work of my colleague Zahid Hassan with basically using angle resolved photo emission. He looks at the bulk states of this compound, which are shaded here, and he also looks at the surface state of this compound using angle resolved photo emission. And essentially, the way they determine that these are surface state, Dan LaSalle is here, so he can answer any questions you have about ARPIS, basically prove that they have basically two-dimensional dispersion rather than being three-dimensional states. Okay, and that's the way in which they can characterize these things as topological, as surface states. Now, as I'm sure you learned here, once you have this inverted band structure, you have to have an odd number of Fermi crossing for these surface states for you to have a topological surface state. And this is the experimental result, which counts these crossings. That the experimentalists basically say that there are 5 crossings for this compound. Okay.
You have to be really initiated to distinguish 4 and 5.
I think initiated or do a lot of experiments to say that there are actually 2 bands there. And this is one piece of information. The other piece of information, it comes from spin resolve ARPIS, which basically tells you that as you go around, so this is looking in the 2-dimensional momentum space, right, kx and ky, and you're looking at basically the Fermi surface, right, at the chemical potential, and these are the different pieces. So this is out here. This is the one, I believe. This one is actually the one here. This is out there. And they made some measurement of the spin texture of these bands, showing that the spin texture was actually changing as you go around here. This is what was basically available. So this is the point where we got interested in doing this experiment. Now, this is a lot more complicated than a surface of copper, Fermi surface, right? You have a lot of different pockets, and it's not just a simple parabola with a circle giving us basically the contours of constant energy. So in these experiments, what we had to do was really push the resolution of this type of experiments to look at very, very large areas of the sample, because at the end of the day, we are taking a Fourier transform of these STM maps. So the larger the picture you have, basically you can resolve all the different wavelengths that could be in this picture. Okay. So these are very painstaking experiments, and if you then Fourier transform them, this information, you see that, so this was the first set of studies. It's kind of almost looking like the kaleidoscope of different wave vectors that make up this picture that you're looking at. Okay. So you might think that this is completely hopeless, right? So there are so many wave vectors here and so many interference patterns, and in some sense, it shouldn't surprise you. So what I've done is taken one slice of Zahid's data here and basically reproduced it to give you something that has a symmetry of basically the Fermi contours of the surface states. So this is what the Fermi surface looks like. And now you can basically ask the question, what should the STM measurement see? Okay. So if you're an electron and you live on this Fermi surface, as we just discussed, you can, if you hit a defect, you can scatter and explore all the different wave vectors that are available, right? So a simple way to make progress is just to simply take the ARPIS data and autoconvolve it with itself, okay? With a scattering wave vector Q that separates your initial and final state, okay? And you can do this, but if somebody gave you the ARPIS data, you can actually do this, and this is what you should measure. So of course it has sort of a symmetry of what we looked at in the experiment, but you notice that out here there is quite a lot of suppressed scattering compared to what is seen in this picture. So this picture is just the auto-convolution of the ARPAS data, nothing more. But of course, what we have to do is we have to put in the fact that we are dealing with a topological surface state. So what did we do? So what we did was we basically went in, and so this brings me to the question that was asked about 4 or 5, or how many band crossings do you have in this material. Basically, the spin information was known about these 2 internal Fermi pockets. Okay. Basically, out here, there was nothing known about what the spin texture of these surface states should be out there. Now, as I'm sure you learned here in the theorists lecture, basically for this thing to be topological, you have to have an odd number of this sort of spin texture in these bands. Okay, so that's what we assumed. This is what we assumed. This was known, and this we assumed. And essentially, from that, we can then just simply put in here a matrix element having to do with the spin texture of the Fermi surface. Okay, so the spin texture is going to suppress the scattering considerably, and this is what happens. This is the joint density of states from the auto-convolution ARPAS. This is including this matrix element. So now if you look at these 2 pictures, you start to see, oh, okay, this is starting to look like the experimental results. You can actually take the high symmetry direction of these pictures and sit and compare them together. So here's the experimental data in the middle. And this is the experimental data from ARPAS, ignoring basically the scattering matrix element and ignoring the fact that you have an odd number of spin textures Fermi surface. And then here is what you get if you take that ARPAS data and include all that. And it's the comparison between these 2 that basically tells us that we are on the right track here. And this is sort of the first evidence we had of this sort of absence of backscattering, because essentially what you have here is scattering between these states and these states is forbidden. Okay, that's not allowed. Now, we can have scattering between these states and these, and this is what gives rise to all these different signals that you see in the experiment. All right? Right. Of course, you can go into the details. It's like reading tea leaves. You can go ahead and read this in all sorts of great detail. Yes. Yes. So it's suppressed. It's basically suppressed because of the angle between the spin of those 2 states, but it's not forbidden.
Can you include those terms?
Yeah. It's just simply an angle between the 2 spins. It's very simple calculation. Okay. Nothing very fancy here. Okay. All right. Now, I like to, so this was done in great detail. And the reason I like to show this is there are many of us in this field who work on trying to make STM very quantitative and compare it to different kind of experiments. And this is what you get if you actually really do this seriously and compare basically the different wave vectors that you get from STM to the ARPAS studies, okay, using the model that I just described to you. Basically, you can measure the energy dispersion of each of these wave vectors in the STM. So this is just a line cut in one of those fancy pictures where the height here is the color scale that you were looking at. And you can see features are dispersing, Q vectors are dispersing with energy as the Fermi surface is changing, the contours of energy is changing. And here, what we have here is lying on top of the STM data is what you expect from the ARPAS measurement measured on exactly the same sample. Okay. All right, so that was very complicated, bismuth antimony. Then the field got relatively quickly simpler by the discovery of bismuth telluride and bismuth selenide and the different cousins, in which you basically have one Dirac cone, essentially one surface state, one band crossing, and the spin texture of that band crossing being the helical spin texture that we expect. So these are ARPAS studies from my colleague Hassan's group and from a group at Stanford. And this sort of snowflake feature has to do with the fact that the band structure of these Dirac electrons is not really quite isotropic. In fact, there is some bending of these things as you get up in higher and higher energy. Okay? And you can do STM on this compound as well. Okay? It's considerably more simpler. Okay? So you have a Fermi surface that looks like a snowflake, I guess, if you like. And you're basically scattering around this Fermi surface. Okay? And now you can do the comparison of the experimental results there with the theory as well. So here are just movies showing you how the density of state basically changes as you change the energy of electrons, going very high in energy at where we started and going all the way to the Dirac point and then below it, or this is near the Dirac point. And I'm going to get into this in a second when we talk about disorder. So you can already see, let me run that movie again. You can already see that here you see very well defined interference wave vectors, and then when you get down close to the Dirac point, you start to see the pictures essentially break up and give you very disordered looking real space maps. Questions? Okay, so here is our simplified Fermi surface of this of bismuth antimony or bismuth selenide. They all look basically the same. And as you go closer to the Dirac point, basically it becomes more circular. As you get far away from the Dirac point, it develops this sort of anisotropy. And I think it was Leon Fu that first proposed that this anisotropy itself can also be reflected also in the spin texture of the surface electron. So what we started with was just the one thing going around in a circle, electrons and momentum and spin being locked together. And now here you have also an autoplay component of the spin as you go around this Fermi surface. Okay, and this turns out to be key because basically that also forbids your scattering processes of these surface electrons. So you not only you have basically to include in-plane and out-of-plane spin, and if you do that, basically this scattering wave vector for this part of the Fermi surface starts to look just like what you expect from the ARPAS measurement if you put this spin-dependent density of state scattering. Yes?
If you look at the scattering in the angles of the
Mm-hmm.
still
You're saying this one should be forbidden
from up.
to the bottom. So let's see. Yes. So K bar. No. So hold on a second. So do I have something wrong? So this is the gamma K direction. I'm sorry. I think this is yeah. So you see here in this direction. Yes, this one. So the two directions. I might have the labels mislabeled. So basically, you have scattering from here to here forbidden, and I think that's this direction. Okay. And it's equivalent. So this direction is also forbidden. Yes. No. Okay. Excellent. So I think here. Let's see. No, that's a good question. See, do you see how these two parts are sort of flat relative to one another? This is actually the critical part of this. Is that here you can always find a wave vector nearby, which you can scatter into, which you're not forbidden. Whereas here, these two sections being very flat relative to one another. So this is just taking this Fermi surface and convolving it with itself and putting this spin texture right on top of it. So the fact that these guys are flat and this guy is not, that makes a difference in this experiment. Does that make sense? So you have a lot of wave vectors that are the same here. And here, if I just go a little bit off, right, I can scatter from this point. And this is kind of a key thing about these scattering wave vectors in TIs. It's a sort of a set of measure 0, right? So if I have a circle and I say, oh, backscattering is forbidden, it's just between one wave vector and its exact opposite. If I just go a little bit off, it's allowed, right? Yes. Exactly. So the fact that you have these flat regions, it allows you to actually probe this property, which you wouldn't have when you have the circle. In fact, look at this. So this is the scattering pattern. It's very well defined. It gives this nice circle. But now I go into the Dirac cone. Here, backscattering is also forbidden. But you see signal, because you can just go a little bit off, and that's allowed. In fact, unfortunately, in these papers, they didn't have enough signal to noise to see that. So they just thought, oh, it just disappears when you go into the circle region. It doesn't. Yes. All right. Good question. Yes.
So, what would determine the diameter?
The circle? So it's basically the Fermi surface, the Q vectors that connect the different regions.
The lower part, the Fermi surface is circle.
Yeah, so this is like close to 2kF. So if you actually do the calculation for scattering, like we discussed earlier for copper, there is this sort of singularity. Okay. Now if you do it with TI, the singularity sort of washes out, but you still get the disk. Does that make sense? Because all the scattering wave vector, which are slightly a little bit off than 2kF, they're all allowed. That makes sense? The one exactly at 2kF is should not be there. It's very hard to do that in this experiment to see the background. If you do a comparison, it's very small difference. Good.
You do a magnetic impurity.
Great question. So we spent 2 years to do this, and we didn't get anywhere. I'll show you the results. It's very subtle. If you put the magnetic impurity, that term should come back, and we couldn't see it very clearly. Yes. Good question. So
this T function, what model, what method do you follow?
a very good question. So the wavelength of the electrons is much bigger than the size of the impurity. And I'm sorry, I don't have the topograph. But if I showed you the topograph, you will see the defects as being almost atomic. And they will have the symmetry of the surface. Okay? So there is some filtering going on there, but I don't think that's a big role because the electron wavelength is much bigger than the size of the impurity. Good question. All right. Now, so that's backscattering, but let's talk about reality. What do disorder do to TIs? Well, it does the same thing it does to any semiconductor. Basically, you create charged impurities, which locally shifts your band structure. Okay? But so we've done some studies looking at, so these are these pictures that we were Fourier transforming, right? And what we found in this picture is that if you go down and look at the electron waves as you get very close to the Dirac point, you can see these puddling things going on here. Okay? And essentially, your chemical potential in these samples are varying as a function of position. Sure, we can make samples that are better and better and better, and we have really improved the quality of these samples over the last 10 years. But this is what defects do to any semiconductor. Essentially, you will create some background potential, which is your Coulomb potential, which is varying the electronic properties of your sample. Now, what's kind of fun is that we can actually see the effect of this not just looking at the conductance map, but actually looking at the wavelengths. Okay, what do I mean by that? So remember, okay, so this is the variation of the spectra. So this is showing you that this is the density of state as a function of energy. This would be a gapped spectrum. This was a simple semiconductor. It has states inside the gap. This is coming from the surface state. And you can see the band structure is just varying on the atomic scale, or roughly speaking. Now what's interesting is this. If I take these pictures and filter them to kind of figure out high and low regions, okay, just to be crude, in terms of potential, and Fourier transform the high and low regions separately, okay, I notice that my wave vectors for scattering is actually a little bit different in the high and low regions of the potential. And you can do this as a function of energy, and this is basically showing you that the band structure is just varying on the atomic scale, not the atomic scale, or on the nanometer, on the micrometer scale in these samples. Actually, let me see what the scale is here. Sorry, there's no scale bar. Okay, I think this is of the order of a micron, or maybe the 10th of a micron. So these two scattering wave vectors are coming basically from two different regions of the sample. Okay, any questions there? All right, so this led us, so this was the first set of experiments. This is an experiment I don't get to talk about very often. It's a very simple experiment. So we thought about, okay, if these are surface states that are supposed to be sort of topological, of course you would expect that if they come to the edge of the sample, they'll just continue on the other surface running down the other side. So how do we probe that? So this is kind of the picture we had of topological surface states, okay? And the question was, okay, if I put a step edge, which just a step edge between two atomic terraces, if your surface electrons in a normal, I'll show you copper, when you come to these step edges, basically you scatter back, or you end up going into the bulk of the sample. You do not go through these step edges at all, as far as I can, as far as we can see with STM. So let me show you some old experiments. So this is just a piece of copper, or maybe it's silver, or they're all the same. Copper, silver, and gold, they all have these 2D surface states. This is an atomic step. Okay, you see a defect here, and you see these standing waves here. And essentially, you can look at the ring down of this wave scattering from this sharp 1D boundary. And these experiments basically showed that there is sort of a pi phase shift. And I think they characterize, I'll show you the results. They basically characterize that there is no transmission between the electrons on this surface to this bottom surface. Nothing at all. It's either getting reflected or just goes into the bulk. Okay, so we did these experiments on antimony. Antimony, remember going back to Kane's original work, antimony has an inverted band structure, but it's a metal because your chemical potential is in the wrong place relative to this inverted band structure. So the bulk is conducting. But the surface has these topological surface states, which is basically, just as is shown here, just as we had in bismuth antimony. And you can study the surface state on antimony, although the bulk is conducting, using STM and ask the question about its scattering properties. And the beauty of antimony is that it's very clean. You can make antimony super clean. So it has this Fermi surface that looks like this. These are electron hole pockets. The spin texture, I've drawn it by hand, which dominates what kind of interference you can have, as I'll show you. And the project is whether you can see a step edge, as I showed you, and you can see whether the electrons from the top, they're transmitted at all through the bottom. Okay. So these turn out to be very, very simple, nice experiments, because as soon as you break a piece of antimony, you get all these steps. And those surface states basically get confined into these little terraces, okay, very much like copper. And so these are the different terraces, okay. This is from this region. This is a cut. This is energy, okay. And this is as a function of position. You can see this is the bottom of the surface state band. This is where the signal starts. You can see that the wavelength is increasing as you go up, just by looking at this picture. Okay. Actually, in this data, you can get a lot of information. So let's look at some sort of a narrow sort of terrace. You have this Fermi surface. You can basically construct what kind of wavelengths you could see in the STM. Basically, the scattering wave vectors that are very intense are coming from this sort of region scattering into this middle and scattering between these two guys. These are the two very intense scattering wave vectors. Why? Because here where the band structure is sort of, where the band is sort of, where it is the end of the band, that's where you have basically large density of states. Okay. Now, what's nice about these scattering wave vectors that you see that they are sort of like quantized, if you like, between this box. But here in this experiment, you also notice something interesting, is that the intensity is changing as you change the energy. Okay? So let's zoom in on one of them. Okay? And what we can do is we can basically look at, this relates to energy resolution question that somebody was asking, but here what we are doing is we're actually measuring the lifetime of the electron. So we have a box, and basically in that box you have a resonance. You can just look at the width of the resonance. And from that width of the resonance, you can basically extract the lifetime of the electrons for different size terraces. Okay? And also you can do this as a function of energy. So it's good, it's parabolic, basically. It should be, it's a Fermi liquid. Okay? But you notice that there is some residual value of this lifetime. Okay? And essentially, this is something that comes in basically because of the probability shows that electron, it gives you a way to basically measure how much the electrons are getting reflected inside your resonator. That's all you're doing. Okay? Okay? So what we found in copper, if you do the same experiment, you find that in copper, 80% of the electrons are reflected, 20% are lost. Okay? And here you have only 40% that are reflected. Now, yes? Yes, it was a one-dimensional Fourier transform. Can you say that again? Is there a theory for that? No, there's no theory. It's just we extracted it from the data. Oh, actually, I think there are 2 or 3 theory papers since this paper came out. I don't actually know the details of what they computed. I should look at it, but it's been a while. Okay, now what we found was if you go to very small terraces, we found something interesting. Of course, here's an experiment where you see a very large terrace, which is too large to even show the end of it. And then you have a small terrace. Okay? Here you can kind of see these sort of confined states, if you like. And out here, you can kind of see these standing wave scattering from this sharp boundary. And this is shown as a function of energy. So these waves are basically dispersing. Okay? And what you notice is out here, just as you hit this resonance, essentially, there is a change in the reflectivity of the waves. Okay? So this is just like your Fabry-Perot interferometer. Okay? It's very simple. And you can basically take this data and you can take this data and Fourier transform it. Okay? And you can see that there is suppressions at the specific values of energy. Let me show you the line cut. Okay, so this is the signal of this scattering wave vector, and you can see that there is this sort of suppression in the reflectivity. Okay. So essentially, this is a nice signature that the surface states for these antimony states, unlike copper, you can repeat this experiment in copper, essentially have some finite degree of transmission, even though there is a very large atomic scale, very large, big scatterer here having to do with just an atomic step. And you can estimate the numbers. The numbers aren't very important. You can remove the background and estimate the numbers. But you find that in our experiment, just as much as electrons are getting reflected almost, the electron are actually transmitted through this step edge. Okay. This Q. Yes, so this energy corresponds to exactly the energy of where there are states inside the resonator. So you make a confinement, you have a states inside, and you have a state outside, and you're just measuring how much your reflecting off and how much you're transmitting through those states. It's a leaky box. Oh, yes. So if you make the step edge different, basically you will get more of these things and you'll see more of these dips. It's very intense in this one, very easy to pick out. Yes?
As a continuation of that, and on the side of the step, always
Oh, that's a good question. So we did try to look for double steps, but I don't think we found any.
really high step.
Yes, I think that the way this surface cleaves, it usually makes just single atom steps, but that's a great question. Or we try to look for other kinds of, like strange surfaces. All right, so let me just skip all this. Okay, how am I doing on time? Another 30 minutes. Okay. So Iris is here. He can explain to you everything about bismuth, right, Iris? Yes. Just get him to just buy him some beer, and he will tell you how he figured out what was happening in this experiment. Right, Iris? Okay, so I got 30 minutes. All right, so let me talk about a more recent experiment. This is an experiment on the wild semi-metals, and basically using the same techniques I just told you about on TIs, looking at the surface states of wild semi-metals, which, as you know, I think you've learned already here, are these Fermi arcs. So let me just remind you very quickly, since I have 30 minutes. So we talked about TIs and their surface states, and of course, the excitement in the field has moved beyond gapped phases to gapless phases. And the prime example of these are Dirac and Weil semi-metals. And of course, a natural way to think about Dirac semi-metals is that is exactly sort of in between, going between the trivial and a topological insulator. You get the situation where you have conduction band and the valence band crossing, and if they're of different characters, as usually are, they basically have this protected crossing. Okay, and now you can go from Dirac to Weil, as you have learned in this summer school undoubtedly. There are two different ways to do it. You can basically either break time reversal symmetry using basically like a magnetic field, okay, or you can break inversion symmetry in your crystal structure. Okay, so these are now band structure of the bulk states. Okay, and you basically go from these double copies to these single wild copies, these handed states. And the thing that we found kind of interesting to think about, and I don't know how much you've heard in this summer school, is that these are, of course, these wild points in the bulk. The thing that's exciting about this is that when you project these wild points onto the surface, they give you these unusual surface states. Okay, so before we had a continuous Fermi surface of the topological surface states, is as if we just cut it in half and put half of the circle on the top surface and the other half on the bottom surface. And so presumably these, the thing that's kind of neat about these is that they are supposed to be connected to the bulk state. So this is a very strange situation where you have an electron living on top of this topological Fermi arc surface states on the top. If you hit this projection of the bulk wild point, it is possible for you to delocalize through the bulk of the sample and come out on the other end. And there is a very nice experiment. I think it's now published, and there's a very nice theory by Ashwin looking at these very unusual orbits, lambda orbits, if you make the samples thin enough, such that basically the distance between the top and bottom of your surface is within a mean-free path. Okay. So there is some experimental evidence for this from James' analysis group. So we became interested in this problem as soon as people started to talk about these Fermi arc surface states. And there is, besides this unusual quantum oscillation experiment, there was also something that was already in the literature. This was computed for the iridates. And the iridates are example of as you know, one of the, probably heard here from Ashwin and Leon and others. These are some of the first examples of these wild semimetals. And this is actually now you're all experts on quasi-particle interference. This is basically an experiment proposing that if you made your sample, let's say, thick or thin, basically the interference pattern that you measure in the top surface would be different, because just as that a magnetotransport experiment explores both top and bottom surfaces, scattering experiments could explore bottom and top surfaces. So this is an interesting thing to think about, whether you can see it experimentally. And also, as you know, these are, they also have the case where you have scattering between time reverse partners on these Fermi arcs should also be forbidden. And there's also spin texture associated with these Fermi arcs. And that should also play a role in what you measure in the STM experiment. Okay, so let's talk about, okay, so I have, okay, let me tell you about first an unsuccessful attempt. So we first started with cadmium arsenide. So cadmium arsenide was one of the first example of a Dirac semimetals in which our ARPAS colleagues basically cleaved these samples. This is a very, very complicated material. This is the unit cell. I think it has something like 80 atoms in the unit cell. And the surface state, the bulk states can be characterized using ARPAS. And this is what they found, that basically this is the Dirac point in 3D. And the idea is that, whether you can apply a magnetic field and turn this into a wild semimetal with the application of a magnetic field. So we did many experiments. Here's some experiments we did on cadmium arsenide. We also explored this sodium-3 bismuth, which you might have heard about from my colleague Fuan Ong. That's also a Dirac semimetal. So you can see that these samples can be cleaved and STM can be done on them. And one of the technique I thought, okay, so let's go back to our quasi-particle interference. We can do our quasi-particle interference experiment again. And we can read off the wave vectors as a function of energy. We can kind of see something that kind of looks like a Dirac spectrum, maybe. It's not that clear. But one of the other techniques we can use is we can apply a very large magnetic field and basically quantize the bulk orbits and look at the Landau orbits in the density of states and their dispersion as a function of magnetic field as a tool of the band structure of the bulk states. So very much like you do Shubnikov-DeHaas oscillations using resistivity or magnetization measurement, we can use the STM to look at oscillations in the density of state with a field. Except here we have the advantage that we're not just looking at the chemical potential. We can do spectroscopy as a function of energy and look at basically the Landau levels, and if there are split Landau levels due to spin or what have you, you can follow them as a function of energy. So here's an example of some very high resolution data. And then you can take this data and basically analyze it in the sort of the standard way, where you say, okay, I have some sort of a semi-classical quantization that I have, and depending on whether you have Dirac or Schrödinger equation electrons, you basically get either square root of B or different kind of dispersion with a magnetic field. And we could do this very nicely for cadmium arsenide. And this is a very nice example of using STM to actually measure sort of with very high energy resolution, basically the band structure. This is a bulk band structure. I don't know why this is so extremely linear in this compound. It's linear over very many, very large energy window, okay? And I don't think this is really, maybe just an accident of the band structure. It's supposed to be only linear, just near to the rack point, but this is somehow linear over a very large energy window. And that's consistent with what our ARPAS colleagues see as well. Anyway, so I won't bore you with these. We can model this band structure using some, model Hamiltonian, and we could quantize this band structure using application of magnetic field. This is actually work done with Ashwin and Vishwanath and his group. And essentially, you could take these Landau level orbits that we saw, and you can really understand all of these details of this band structure using this model Hamiltonian. Okay, so the bad news here was that because the way our sample breaks, the way it cleaves at an angle relative to the rack points in the bulk. So application of a magnetic field at an angle relative to these points basically doesn't allow us to really get into the wild physics. So this was a unsuccessful attempt, although we can use this spectroscopy to really understand the details. Okay, so that's a little digression there. So let me talk about the inversion symmetric breaking wild semimetals. And this is there are now many different compounds out there, and this family of tantalum arsenide, niobium arsenide, there is a number of them, which were first theoretically predicted to have these 24 wild points. Okay, and these 24 wild points, when you project them onto the surface state, okay, you end up with I think there's some that lie right on top of one another when you project them onto the surface. You end up with this Fermi surface of the surface electrons. These are basically all the different Fermi arcs that you expect to see for this particular material. So this is a theoretical calculation for this compound. I think there are many different calculations in the literature, but they all basically more or less, they more or less look the same, but with some assumptions. One of the key assumptions is what kind of surface termination do you have? And that determines very much in detail what kind of Fermi arc that you will see. Now, what's maybe nice, not so nice, I don't know, it depends on your perspective about this field. Everything that's calculated is immediately measured using ARPAS, and they seem to pretty quickly verify these Fermi surface that I described. These are experiments from several different groups. My colleague Zahid Hassan, Hong Ding, and Yulin Chan. All of these groups basically more or less find these Fermi arcs and Fermi surfaces. Okay? So, you also have spin texture that's now been also characterized for these for these surface states. And the spin textures are shown in this diagram. Now these are sort of artists' sort of vision. This is the actual data. How they go from here to there is not always clear to me. But these are, these are not art. This is the theoretical calculation. These are the actual data which they believe to be consistent with the theory. But I don't know all the details of these measurements, how they actually measure things in 3 dimensions so accurately. Okay, so now our job is to ask the question, okay, what happens when you look at these electrons with the STM? And as I told you, the question we are most interested in is whether there is something special that happens when the electrons basically scatter and go near these wild points. Okay. So let me tell you about the experiment. So we start with tantalum arsenide. We cleave it, and this is what the surface looks like. These are beautiful crystals. They give you very few defects that you can see in this relatively large point of view, field of view. And of course, it's a semi-metal. It has some density of states near the chemical potential. And we can go to work doing basically the experiment I described to you throughout this talk, which is look at different energies, look at electrons as a function of energy. And again, you can see a lot of scattering, a lot of interference of these electrons. And now we can take a Fourier transform of that, and we can see that again, there is quite a large number of scattering wave vectors as a function of energy. So here's what this is what the experimental data looks like. So the first thing you see is this very nice anisotropy even in the surface. Just looking at the raw images, you can sort of see that this direction and this direction are not equivalent in this crystal. Okay. And you can see a lot of wave vectors here. So again, now I think you've seen the first example of TI. We weren't quite as discouraged when we saw these experimental data. And of course, you can follow them as a function of energy and show that they disperse as a function of energy. And so they are really due to interference and dispersion due to the band structure. You can find at least 10 different wave vectors. Okay, so these are just details you can look at. So the naive thing to do, based on what I told you at the beginning of this talk, is to take the Fermi surface of the surface arc states, put on top of it the theoretical expectation for the spin texture, and just compute what the STM measurement should see. And as I showed you, this is very successful in pretty much all of these materials. Okay, once you know the Fermi surface from at least ARPAS experiments, and which is captured by some theory, you can do a very good job. So when we did this, so here are the comparisons. So here's the experiment, and here's the theory, which basically captures the ARPAS measurement. So you can see there are some features that are similar, but one of the things you notice is that there are very large swaths of scattering in these interference patterns that are just simply missing. Okay? So this could be just the theory is just not good, or the experiment shows a lot of signals. So if the scattering signal, this scattering signal here should be weaker than over here, so we should have definitely detected it. Okay. Question. Yeah, towards the center, it's very hard to trust the data. This is the region you're talking about. At very close to Q equals 0, you have sort of long wavelength fluctuations that you cannot completely trust. Then we realized we forgot to put something important in. So I told you about this interference picture, okay? But the idea here in this compound is, okay, you scatter between these Fermi arcs, but if you scatter as you come close to the wild points, basically you become more and more delocalized into the bulk of the sample. Okay? So just think about like a leaky surface electrons. If I put an electron into the states close to the wild point, there is a high probability for it to decay and go into the bulk and never come back to interfere with the electron I put in there to give you the standing wave. Okay? So it turns out that the leaking to the bulk is very tied together with the type of atomic orbitals that you have in this compound. What I mean by that is that if you look at the atomic character, so these are calculations from Andre Bernovic and his group. If you look at the atomic character of the states as a function of energy close to the wild points, you find that 90% of the wild nodes have a tantalum atomic character. Okay, so what do I mean by that? I mean that if I'm an electron and if I end up going into the tantalum states, okay, then I have a high probability of being connected to the wild points in the bulk of the sample. Okay, so what we did was we basically realized something that people who did all these calculations forgot, which is that when you do these computations, this is not like an ordinary surface state, which is just associated with, say, the last atoms on the surface. Okay, this is associated with sort of some set of states, if you like, within the first unit cell of near the surface, And some of these states near the surface are very well connected to the bulk states of the sample. Okay? So we went back and looked at, in the theory, at basically a decomposition of the different states as a function of the depth into the sample. Okay? So we found that if you look at the arsenic states, basically, and you go deep into the sample, you see that the arsenic states are very relatively localized near the surface. This is a log plot, where the tantalum states are very delocalized into the bulk of the sample. Okay, so this comes from the fact that you have 90% of the weight of the wild points in this compound come from the tantalum states. No, this is a theory calculation. I wish we could get the density of, say, as a function of depth. So the cleavage plane here is arsenic, but yeah, it could be. So the other half could be tantalum. I mean, it's not like always they cleave beautifully. So you can have a surface that's not stable. When you cleave the two, one of them could be very stable, and the other one just could reconstruct. Doesn't have to. The one that's atomically very beautiful, well, the one that's atomically beautiful gives you the Fermi arcs that you expect for the arsenic surface. Does that make sense? Almost done. So basically what this decomposition had us do is not to look at the entire, not to look at this entire picture that comes out of a calculation of what the Fermi arc should look like. Even though the ARPAS measurement looks exactly like this or looks close to this, what you want to do is you want to construct a weighted Fermi surface, which takes into account how much the electrons in this Fermi surface of the surface states is leaking into the bulk. Okay? So the idea is, this is what you started with. This picture just ignored the fact that if I put an electron in parts of these Fermi arcs, they would just never have any interference effect at the surface, or they will be very small. And then we begin to, then you start to compute what you should see in the experimental result using this picture. So this picture has not only the shape of the Fermi arcs, not only the spin texture, but also includes the fact that, roughly speaking, as you get close to the wild points, there is sort of a leaking of the signal into the bulk of the sample. And this is the picture that starts to look really like the experimental results. Okay, so that big bar of scattering that you actually observe it starts to go missing, and I won't go into the details of, we can also do a lot more analysis. I'll show you one example of it. But we begin to see that we can understand all of the details of the experimental results of these interference patterns based on this weighted Fermi surface. And you can not only do it at one energy, you can do it as a functional energy. You can do it in great detail. And so this is what you would expect to see if you did not include the decay into the bulk. This is what you expect to see if you include the decay in the bulk. And this is what the experimental results look like in the middle. No, so always in these experiments, the impurity site is very small compared to the wavelength of the electrons. So, well, we see impurities in a lot of different places in the sample, but unless the impurity filters specific Q vectors out, there's no reason that it would matter. Either it would scatter or it would not scatter. But how it would affect these experiments is if it produces a filter. Okay? And the filter effect would have to be very strange, which filters out sort of things in the middle of this pattern. So you have to come up with some diabolical filter to... I'm sorry? It depends on where you are in the Fermi surface. And this is precisely what's interesting about this experiment. So you have these Fermi arcs. And these Fermi arcs, as you move around them, at different places, if you put an electron into them, the lifetime of the electron, you can think of it as a lifetime. The lifetime of the electron on the surface varies as a function of k. Okay? And this experiment is probing that because it just looks at the interference, and whichever q initial and final, where the lifetime is short, we don't see it. Okay, let me skip this. You can do additional experiments, so you can take the image. This goes to maybe Dan's question. You can take the image and you can filter out the arsenic site signal and the tantalum site signal on the top surface, making the assumption about that we know what surface we are looking at. And you can analyze them and compare them to this theory as well in good detail. So that's another thing you can do. Okay. So, I mean, what would be great is if we could find, this is a charge to the theorists, wild semi-metals with very simple Fermi arc surfaces, okay, in which we can actually start to explore this type of non-local kind of transport in our STM experiments. And this is, of course, you have 16 different points. You know, this kind of connectivity is great, but, you know, we're having a hard time, for example, producing experiments where the samples are very thin to actually see the top and the bottom surface of the material basically being connected together. Okay. Okay, so I'm gonna basically stop here and go through the details. So the other thing you can do is actually do these magnetotransport experiments also in the STM. All right, so today it was all about quasiparticles and their interference, and this is kind of very material-based type of topic. You know, we find a lot of different topological materials, and we just go through looking at them with ARPAs, with transport, with STM, trying to tease out these properties. So tomorrow, I'm going to focus on what I like to call at least a model system, where we look at these, you know, sort of very simple materials to try to build a topological superconductor out of them, which is a very different kind of application of all this technology that I told you about. So this is all very material focused. And unfortunately, you have to dig into the details of the band structure of the material to really tease out all these effects. And right now, most of the materials we're dealing with either you're talking about TI or wild semi-metals, they have a lot of material physics within them that you have to disentangle. There's a lot of disorder effect, very complex band structure. So it makes the topic not as friendly, if you like, to theorists as one would like, but perhaps the topic tomorrow would be more friendly. So I will take more questions, but it's a long day. Thank you. Yes?
Possible maybe like the distance from the tip activity layers.
I think the best experiment is to just do a thin sample, because then you would see many additional wave vectors than you had seen before. That's true. Well, I think that if you move the tip closer and further, you're gonna just be more sensitive to what you see exponentially. You might see more additional features. I mean, one of the experiments you could try to do is to try to find we try to find step edges in which you see electrons kind of leak underneath the step edge, depending on the orientation of the step edge, to try to get at some of these layer-dependent physics. But being able to probe deeper into a sample that's even a semi-metal is very difficult. Yeah.
Actually, realize that I miss how it's actually done. How do you resolve K? I mean, you inject a particular energy electron. So how do you?
We see all Ks. We see all possible K initial minus K final. It gives you all different wavelengths in the picture.
But you're measuring a real K.
That's right. We do a Fourier transform, and we see all the K initial minus K final. We don't resolve K. We resolve Q.
No, I understand. So you see real space images that Fourier.
That's right. Yes. It's just the way the sample cleaves. It cleaves by exposing the let me take that back. Tantalum states should be very delocalized. That's what we believe. You talk about this experiment. It's very simple. So what you do is you take a picture, right? So you know where the arsenic atoms are, and you get atomic registry of your conductance maps. So these are energy resolved conductance maps. You have the topography. You just pick out where the arsenic sites are. You keep the signal from those pixels, or you keep the signals from the pixels in between them. That's all you do. Well, that's how this experiment works. And this is the natural plane at which it breaks. I mean, these are very hard compounds. It's not like graphene. I wish they were like graphene. Right. Yeah, I don't think there's anything universal about the way they're. Yeah. So, okay, if you could do an experiment where you applied the field and you created the Fermi arcs by breaking time reversal symmetry rather than inversion symmetry, then if you change the orientation of the magnetic field, you rotate the Fermi arcs. That's the experiment to do. Yeah, that would be much more controlled. You're not relying on the structure. Good idea. That's what it looks like, I believe. Yeah, if I remember correctly. Good. I'm around. Good.